So today we'll do exponential growth and decay. So previously we see the exponential function. Let's differentiate it first. dy over dx, we get e to the power of x. When we differentiate exponential, we get the same function. Now if we replace it by e to the power of x by y, we can write it as dy over dx equals to y. Okay? So the derivative is equal to itself. Now, when dealing with rates, the result looks more familiar if the polynomials are replaced by q and t. So instead of y equal to e to the power of x, we got q equal to e to the power of t. And we'll do the same thing again. We'll do dq dt, which is a rate of change of quantity. And that's equal to e to the power of t. And if we write it again, that can be written as dq dt. The rate of change of quantity is equal to the quantity itself. And of course, we can make the result more flexible by changing t to kt, where k is a constant. So if I differentiate e to the power of kt, it becomes e to the power of kt. Actually, it becomes k times e to the power of kt. Like that. And I could replace this by q, so therefore the derivative of the quantity is equal to a constant times the quantity. So we say that the rate of change is proportional to the quantity itself. Okay, so now we have a more general formula for exponential growth and decay. So a more general formula is q equal to q0 times e to the power kt, where q0 is the initial quantity, the quantity at time 0. We can prove that this works for this equation. So this equation is a representation of exponential growth and decay. So let's prove this. So we're going to differentiate q, and because q0 is a constant, we ignore. And then when we differentiate e to the power of kt, it becomes k e to the power of kt. Yes? All right. So after that, we'll take the k out. So write k times q0 e to the power of kt, like this. And the reason why I do this is because this whole thing is q. This whole thing is q. So I could replace it by q. So k times q. Okay? So the rate of change is proportional to the quantity. All right. So we need to know how to do this in exam. This is examinable. How to prove this result. That the rate of change is proportional to the quantity for the exponential growth and decay. And remember this general formula. Let's highlight this. So you need to remember that the general formula is, so I use a highlighter. So this formula you have to memorize. This formula you have to memorize. Okay. All right, good. After we do this, we're now going to do some problems. But before we do some problems, we need to learn how to use a calculator. So have your calculator out. You need to use a calculator for this exercise. So all the questions, you need a calculator. So get your calculator out. In this topic, in this section, we need to know how to store numbers on a calculator. We'll know how to do that before. Let's revise this. So let's type in 3 over 2 times by ln 2. Right? So in this topic, you will get a lot of these numbers, which you can't change to a fraction. So I want to store that. And to store this, you look at this result, shift RCL negative. So press shift RCL negative. So it stores into the polynomial A. And to access that polynomial, you press alpha negative. That gives you the A. So if you press equal, it gives you that number. Now, what if you turn it off and go shift off, shift off? It doesn't turn off, but then if you turn it off and turn it back on again and press alpha A again, it still gives you the same answer. Okay, it stores there indefinitely. Okay, so what we do is we're going to use this to help us to do the question. So remember how to store things. So remember it's shift RCL negative. Okay, Alright, of course you don't have to store into negative, you can store into B if you want to. So if I say 3, actually it should be 3 over 4. So 3 over 4 ln 2 equal, and you can store into B as well. So shift RCL B. So it stores into B. And if I want to access what B is, alpha B equal. Okay, like that. Alright, after we do this, we're going to do some questions. Alright, let's look at example. So the rabbit population P on a goat island was estimated to be 1,000 at the start of 1995 and 3,000 at the start of 2000. The population is growing according to the natural growth, which is the exponential growth formula, and where P is the rabbit of population, T years after the start of 1995. So the first question asks you to prove this result. We know how to prove it before. Let's do that again. It's very easy to prove. dp dt first equal P0 k e to the power of kt. That's your first step. Second step, write the k in front, P0 e to the power of kt. And then you just have to replace this by P. So you write equal to kp. So the result is proven. So you have to show these steps to prove this result. After you do the steps, you have to find the value of P0 and K and sketch the graph of T. So to find P0, now remember P0 is the initial quantity, so P0 is the number of rabbits in 1995, which is 1,000. So write 1,000 as P0. Once you do that, you write P equal to 1,000 e to the power of kt. Basically using this formula. That's your formula. And to find k, use the second bit of information. In 2000, the number of rabbit is 3,000. So in 2000, year 2000, you get let's say year 2000. Year 2000 will be 3,000 rabbit. Now, what's the value of t for that? That will be t equal to 5. So it's substitute t equal to 5, that's the value for P to work out K. So you write 2,000 equals to 1,000 e to the power of 5K. Then you can solve for K. Let's solve for K. So how do we solve for K? We divide both sides by 1,000 first. So divide by 1,000, divide by 1,000, cancel the 1,000, you get 2 equal to e to the power of 5K. Yep. Oh, yep, sorry, 3,000. Thanks for that. Okay, thank you. 3,000, so that will be 3. And then we're going to ln both sides. ln 3 equal to ln e to the power of 5k. Whenever we want to find the power, you use ln. And then ln brings the power down. That's why we use ln. And ln e is 1. So you write 5k times 1, which is ln 3. So k equal to 1/5 of ln 3. Now, if you do it on a calculator, it's going to be ln 3. Make sure you close the bracket, divide by 5, you get this, which is long thing. You want to use the whole value. So you're not going to write everything down. So you just leave it on a calculator. So press Shift, store A, stores into A. Okay, we're going to access this later. Okay. All right, so we found K, we found P0. Now we can draw the graph. So let's draw the graph. You don't need the negative value because the number of rabbits is positive, time is positive. So let's try to draw the graph. Now remember, it starts as 1,000 in year 0, and then after 5 years becomes 3,000. So 5 becomes 3,000. So put a dot. So you already have 2 dots. So your graph will just go like this. That's your exponential growth graph, which is the normal exponential function you've seen before, except I do not graph the values on the left of the vertical axis because it's negative. We don't have negative time. The graph just starts from 1,000, just stops there, and then just continues from there. Okay, that's exponential growth graph. Okay, after we do this, we can then answer further questions. Let me see, what do I do? Next question, see how many rabbits are there at the start of 2003? So you need to be careful is that you have to know what the t value is for 2003. What's the t value? 8. Yep, because you can just go 2003 minus 995, which is 8 years. So now you have the formula. You just substitute t equal to 8. What's the population of rabbit? So write p equal to 1,000 e to the power of k times 8. Now remember k you found already from this part. So when you do it on a calculator, you do this. You do 1,000 times by exponential. K is alpha a times a. Right, like this, instead of typing 0.2 something that we did before, press equal, right? Because otherwise you have to type this digit in, which is long. So you just store into a, gives you this answer. So which is 5,700, and we round to the nearest 10 rabbits. So nearest 10 rabbits will be 800, isn't it? 5,800 rabbits. Okay, 5,800 rabbits to the nearest 10. Nearest 10. All right, any question? Okay, so we found how many rabbits there are. After we do this, we can then do the next bit. Now, the next question is, when will it reach 10,000 rabbits? So we'll do the same thing. 10,000 equal to 1,000 e to the power of kt. Okay, you can just leave k as it is because I've already stored that on a calculator. So to find out what t is, you divide both sides by 1,000 first. So you end up getting 10 equal to e to the power of kt. And then you're going to ln both sides. ln 10 equal to ln e to the power of kt. Okay? And then you bring the kt down, which is kt ln e. What's ln e? ln e is 1. So we end up getting ln 10 equal to kt. T equal to ln 10 over k. Remember, k is a. So on your calculator, just type in ln 10 close bracket divided by k. Now k is alpha a, like that. Press equal. So it takes 10 years. 10 nearest month. So 10 years and 6 months. So let's see, how do I do this? So it minus that by 10 and then times by 12 because 12 months in a year. So about 6 months. So 10 years and 6 months. So 10 years and 6 months. Okay, good. All right, any question? 10 years and 6 months. Okay, good. Which is, let's move on to the next question. And then we'll got some more further questions to do. Okay, so find to the nearest 10 rabbits per year the rate at which the population is increasing when there are 8,000 rabbits. We have to find the rate. Now there's two formulas for rate. The first one is dp dt equal to kp. Or the other one is dp dt equals to the one we just proved during the formula, this formula here, kp0 e to the power kt. Let's write that down, which is k times p0 e to the power of kt. So we've got these two formulas. Now which one will be useful? Because they tell you how many rabbits there are, 8,000 rabbits, it's easier to use this formula. Okay, so let's do dp dt is equal to k times 8,000 rabbits. Now we'll know what k is. K is that 0.2 decimal. Let's do that. So you do 8,000 times by alpha a. Oops. Alpha a. Gives you 1,500 and nearest 10 rabbits. So it'll be 1760. So approximately 1760 rabbits per year. So when there are 8,000 rabbits, the rate of change is 1,760 rabbits per year. Okay, now if you are given the time instead, you should use this formula. So use dp dt, which is equal to k times 1000 e to the power of k times, now what's the e will be 2, right? T equal to 2. Like this. And then you just use your calculator. So you do k times 1000 times alpha e, k again, times 2. That's the rate of change. So approximately 340 rabbits per year. 340 rabbits per year. Any question? Okay, like that? All good. Okay, after we do this, we'll move on. There's still like 2 more questions to go through. Alright, so it's pretty easy, the exponential growth and decay. So it's very straightforward. Usually students like this topic because it's very straightforward. Okay, let's move on. Next question. And in the exam, you will get a question like this every year, so it's very good. Our next question, the price P of a pair of shoes rises with inflation according to this exponential growth formula, where T is the time in years since records were kept. And the first part, they always to ask you to prove something. So that's something very easy to do. So you can just do it. So dp dt equal, and just a 3-step answer. Okay, so I'll leave you to do. Have a try. dp dt. Okay, so it's very easy. Just pull the k down. P0 e to the power kt. This thing is p. And done. Finish. Okay, that's all you have to do. Where P0 is the price at time 0 satisfies the given differential equation. Okay, good. All right. So the differential, this is called the differential equation. So this equation satisfies the differential equation. Okay, so this thing here, this equation satisfies this. Okay. All right. So after we do this, we're going to do the next part. If the price doubles every 10 years, find k, sketch the curve, find how long it takes for the price to rise to 10 times its original price. Okay, let's do this. So this part, they don't tell you what the initial amount, it's just P0, isn't it? So what you do is this, you say price doubles every 10 years. So that means when T is 10, the price will be double the initial price, right? The initial price is P0, which is a constant. So now we're using this formula, P equal to P0 e to the power of kt. I could now replace the P by P0. Double P0 equals to P0 e to the power of k times 10. Because after 10 years, the price got double. Okay, so what do we do next? We have to divide both sides by P0. Cancel, cancel. And you're going to get 2 equal to e to the power of 10k. Like that. And then what do we do after this? We're going to solve for k. So we'll just ln both sides. So k, ln2 equal to 10k. Right? You can just skip the ln is 1. So k equal to ln2 over 10. Again, you have to store on a calculator. So you just do ln2 close bracket divide by 10. And just press shift store RCL. Okay, so it stores it straight away, 0.069. So that's the K. And what do we do? That's it? Okay, good. Now, maybe what you could do is maybe to also write down the value, because sometimes they do ask you to find k correct to 3 significant figures. So you may have to write down the value. So it's equal to 0.0693. Sometimes the question will ask you to calculate what that is. So make sure you write down the values. Okay. And then find out how long it takes for the price to rise 10 times its original price. So that means now you have to find out t equal to question mark when p equal to 10 times the original price. Okay, so let's do that. So you go 10 P0 equal to P0 e to the power of kt, and then divide both sides by P0. They get cancelled, which end up getting 10 equal to e to the power kt. ln 10 equal to kt, t equal to ln 10 divided by k. Alright, good. So you just use your calculator. So do ln 10 close bracket divide by the alpha a, like that, equal, takes 33 years. So approximately 33 years. 33.2. So how long it takes for the price to rise to 10 times? Yeah, 33 years. Okay, 33 years. And now we have to draw the graph. Now to draw the graph, we can use the information we found earlier, t and then p, which is 0, like that. And then it starts off with p0. So p0 is the initial amount. And it took about 10 years to double. So after 10 years, it got double. So let's put 10 here. It got double to p0. So put a dot. And then it took about 33 years to make it 10 times bigger. That's a bit hard to draw, but about 33 here become 10 times. So maybe very high, so 10p0. Somewhere here. So it goes up like this. Okay. Alright, good. So that's your graph. So all exponential growth graphs look the same. They all just goes up. So the only difference is where it starts. Okay. Alright, done. Any question? Alright, after we do growth, we'll do a decay, and that's it. Okay, so there's growth, there's also decay. So we'll look at examples where decay is used. And the formula for exponential decay is exactly the same, very similar. Okay, so for exponential decay, we just have to change the k to a negative because it decreases instead of going up, right? Because it's decaying. So instead of k, you have negative k here, like this. And then, like before, m0 is the initial quantity. M0 is the quantity at the beginning. And then it is also perfectly acceptable to not to use the minus sign. You can just write it like this, without the negative. In that case, k will be negative. Okay? If you put a negative there, k will be positive. But it's the same thing. Okay? You still get the same equation. All right. So we're going to do an example where exponential decay is used. So we'll go to the next question, next page. All right. So one example where decay is used is chemical compound, which decay a radioactive element that decays. So if you do chemistry, you know about half-life, but you don't have to know chemistry to do this question. So let's look at this. So we have a paddock that has been contaminated with strontium-90, which has a half-life of 28. Half-life means that it takes 28 years to decay to half of its amount. So when t equal to 28, the amount will be half of the initial amount. That's what half-life means. It takes 28 years to reach half of its life. This means that exactly half of any quantity of the isotope will decay in 28 years. M0 be the original amount mass present. Find the mass of strontium-90 as a function of time, then sketch the graph. Okay, so what we do is, first we write down m equal to m0 e to the power of kt. You don't need to have a negative sign, you can just put a k there. And then we're going to find k. Now, that's where you have to use this information here to find k. Okay, so when t equal to 28, the amount of strontium will be half of the initial amount. Okay, they don't tell you what the initial amount is, but we don't need to know that to find k. We'll just substitute. So right, 28 equals to half m0, half of m0 equals to m0 e to the power of k times 28 years. Okay, after 28 years is half of the initial amount. And then what you do is, like before, divide both sides by m0, gets cancelled. So you end up with half e to the power of 28k. And you just have to solve for k. How do we solve? So we'll just go ln half equal to ln e to the power 28k, which the 28k will go down, and the ln e becomes 1. So 28k ln half. And then to find k, you just go ln half or ln 0.5 over 28, which you do on a calculator. Okay, let's do that. So we'll do ln 0.5 close bracket divide by 28 equals -0. Yes, so see it's negative for exponential growth and decay. For decay, negative 0.024, negative 0.024 ... Okay, which I'm going to store onto the calculator. Shift RCL A, so A calls this value. Once you do that, we can write down the formula. So therefore, the formula for the amount of strontium is this KT, and just write down what K is. K is approximately negative 0.024. Okay, that's the formula for the decay. Okay, then we have to draw the graph. So we'll draw the graph. So we'll draw x-axis and the y-axis, M and T. Okay, and because it's decay, so the initial amount, let's make it a bit higher. That's M0, right? Because you won't go higher than this point, and it takes 28 years to get half of its half-life. So you get a point here, and then it goes down from that point, goes down, and there's an asymptote. So it's just approaching 0. Okay, as time goes by. All right, that's your graph. Pretty easy. So that's an exponential decay graph. All decay graph will look very similar. You start with initial amount, just goes downward. Okay, and just indicate, I'm going to point that you pass it through. All right, okay, so we've got 2 more questions to do, then we finish. Okay, so we'll do the next bit. Find what proportion of radioactivity will remain after 100 years. So all you have to do is to substitute 100 into the formula. So you go P equal to 100, M equal to M0 e to the power of K times 100. And you just use your calculator. So what you do is, because I don't know what M0 is, just do this on a calculator. So we're going to do exponential K alpha A times by 100, like that. 0.08411, 0.08411, ... But they want it to be in proportion, which is percent. So what would that be? We times by 100, which is 8.4%. So which is 8.4% of the initial amount. So you say, therefore, 8.4% of radioactivity remains after 100 years. So even after 100 years, it's still very radioactive, still dangerous. 8.4% remain. Okay, all right. All right, now we have to find out how long it takes for the radioactivity to drop to 0.001% of its initial value. Answer to the nearest years. So we do the same thing. We have to go like this. We have to find T equal to question mark when the M equal to 0.001% of the initial amount. Okay. So what do we do? Okay, so let's write down this. So write 0.001% of M0 equal to M0 e to the power of KT. Okay, and then we're going to divide both sides by M0. That will cancel like that. And then you get 0.001% equal to e to the power of KT. And then we're going to ln both sides like before. So ln 0.001% equal to KT ln E, and ln E is 1. So therefore T equal to ln 0.001% divided by K, which you can use your calculator. So let's do that. So ln 0.001, but there's a percentage button. Shift bracket gives you percentage. Close bracket divide by, remember what A is. A is decay, equal 465 years to the nearest E. Okay, 465 years. 465 years for you to drop to that level. Alright, so it has a lot of applications. So you see exponential graph has a lot of application in real life. Okay, good. So what you do is you can start the exercise from the Cambridge booklet, which is exercise 6G today. Okay, you can start.